the focal length of the concave mirrors, the second phase. Now what we intend to do is to change the position of the object, which is essentially this distance from this mirror to the object. This object distance, we want to change this and then see where the image is formed. So the image is actually the distance between, the image distance is the distance between the mirror and the screen. This is the image distance, and this is the object distance. So we are going to change the object distance and focus on the screen. So the screen also has to be shifted, and the corresponding values of u and v will be tabulated, and then we will use the mirror formula or other graphical methods to find out the focal length. So the first reading is, you can see that you can see that as I shift the screen, now this is typically has to be done in a dark room because it's not quite visible. This is out of focus. As I bring in the screen closer, I get a sharp image, and this is probably a position where the image is sharp. So this is my object distance from here to here, and then from here to here is my image distance, V. So I'm going to take variations of these readings and put it on the blackboard and get back to you. Remember this, and this is when the object is between the focus and the radius of curvature. Conversely, when the object is far away, then we'll get an image which is you can see the image. There's a sharp image on the screen, and it's very small and inverted. So the object distance is beyond the radius of curvature, beyond the center of curvature, and the image is now inverted, and it's out of focus. There's a wind as a result. Okay, yeah, there is the image. So now in this particular case, the image distance is small. The object distance, as you can see in the background, the object distance is large. So we have adjusted the object distance at 50 from the mirror. So this is the mirror is at 0, the object is at 50, so u is 50, this is beyond the center of curvature, and we are going to adjust the screen so that a sharp image, see the out of focus, and as I bring it closer, the image is brought to a focus. And in this position, we'll observe the image distance, it is 32.5. when this is at 0. So 32.5 is our, maybe 32 or 33 is our image distance when the object distance is at 50. So the rest of the readings, once I complete, I'll report back. So essentially, we are going to change the object distance and bring the object to the image to a focus and get the image distance. This is the next reading. The object has been placed at 60 centimeters from the mirror, and when we adjust the out of focus, this is out of focus, so somewhere in between, somewhere here probably it's in focus. So in this position we'll take the reading, and the reading is 30. So image distance is 30, object distance is 60. This is our final reading. The object now is kept at a distance of 70 centimeters from the mirror, which is at 0, and the image is focused on a screen which is now at a distance of out of focus, so somewhere in the middle. This is how you adjust the screen to get it out of focus and back to focus, somewhere here. And that gives you a reading of 26. So this then is our final tally. Notice that we have taken two values of half the values of object distance between the focus and the radius of curvature, and their corresponding object image distances. And three values we have taken beyond the radius of curvature. Here you get inverted real images. These give you magnified real images. In any case, we have to use a real image because we're using a screen. We cannot get the object between the focus and the pole. Then we'll get a virtual image which we cannot catch on a screen. So that's why we are using this formula, which is applicable only in the case of real images. And from these we are going to calculate the focal length and finally take the average. So that is the end of the experiment.